All right. Okay. So let's start. So today we'll look at what is inside a modern desktop. Okay. And I have taken up Dell laptop, Dell desktop for that. For today's study, and as I discussed, I we will also look at sometime in future architecture of a mobile handset. Okay, so obviously, if you see the specification of your desktop, and you can easily see in my Mac Pro, I can just go to specifications and then see it about this Mac. Uh, okay, and in your if okay, Kartikeya Sharma, you are not mute. Okay, all right. Please mute yourself. It will disturb others otherwise. All right. So you can see what is the configuration of your machine. What are the specifications? And I think your first assignment that I will post today will be based on, you will have to write down what is the specification of your laptop and mobile. Okay, if you have desktop, you write down it for desktop. Okay, all right. So processor, obviously it has processor, memory, and then it will also have a bus, it will have network, some ports for doing IO, and some sensors. So these are the main components. So processor that is there in this desktop is 10th generation Intel Core, and number is i9-10900K. uh, and further specification says that 10 core, 20 M cache. Clock varies between 3.7 gigahertz to 5.3 gigahertz, and it has 20 threads. Okay, all right. Memory, it says that solid state drive, hard drive is storage accelerator, DRAM. Then chipset is DRAM, bus with bus width is 64 bits. Then it has a bus, which is PCIe. Okay, third generation. And network is obviously each laptop will have Ethernet, where you can connect to Ethernet cable. Okay, and also it has a wireless LAN or Wi-Fi, what we call as, right. And latest one is Wi-Fi 6. So most of you, if you have bought laptop in last 2 years, then you would be having a Wi-Fi 6 interface as well. So you will see that all these interfaces are available. It means that somebody who has, whose router does not support Wi-Fi 6, a old router, then possibly one of these will work, right. Okay, and there's a Bluetooth 5.1. The question I may ask you is, what's the difference between Wi-Fi and Bluetooth? Okay, tell me.
Sir, Bluetooth can be used to connect to nearby devices, whereas Wi-Fi can be used to connect to all the devices which are in turn connected to Wi-Fi.
Okay. Uh,
The range of Bluetooth is quite less, like it's up to 5 meters
mhm.
optimally.
Yes. What else? Good, good. Both points are correct.
The rate of data carry is for Bluetooth like 1 to 2 Mbps, but Wi-Fi has quite big
Very good.
bandwidth.
That's also correct. Something more?
Frequency range is different.
Yes,
Uh,
that's also
Sir,
correct.
Wi-Fi
energy,
allows you
energy,
to,
energy usage, man, sir, maybe.
Mm-hmm.
sir, Wi-Fi allows you to connect to the internet, but Bluetooth can't.
Well, repeat.
So Wi-Fi allows you to connect to internet, but Bluetooth doesn't.
That's not correct. See, Bluetooth and Wi-Fi is basically layer 2 technologies, right? Anything you can run over that. I can connect my other machine through Bluetooth and run internet over that. So we will also study internet uh, as part of this course, and we'll see, we'll just touch upon that, right. We'll see what actually, because we'll study local area networks and also Wi-Fi, and see how internet runs over layer 2 technology. Internet by itself runs over something. It's like, trucks carry some stuff, parcels. Now so basically trucks are layer 2 and the parcels that go over that is layer 3. Okay, we'll study that, but that also defines the routing. So essentially IP packets can go over any layer 2 technology in general. Whether you send it or not for your application, that's a different aspect altogether. Okay, so what you have said is all correct. Ethernet and see, Wi-Fi has been designed, as you rightly said, to connect devices in local area network. It could be say 100 meters or less, depending on what kind of router or antennas you have. Okay, and it works at very high speed, as you rightly mentioned. Wherein Bluetooth is largely is a low power stuff, right? I mean, it does not consume so much of power as Wi-Fi does. So essentially, both are of course, I mean, wireless technologies. Stacks, their actual implementation is also very similar, but Bluetooth is not designed for very high speed communication as Bluetooth is, right? And Bluetooth power requirement is very, very less. So for example, your Bluetooth interface on mobile should not consume too much of power. Otherwise, if you listen to, for example, music over Bluetooth, and you're connecting your mobile through Bluetooth to laptop or some other device, then it may go for many days, 10 days or something, or even more than that. While if you connect through Wi-Fi, any other device, that your battery may not go for so long because Wi-Fi consumes more power. So these are the main differences, but we'll go into detail if time permits towards the end of the course. Okay, then we have bus. Bus, see, we have different components in a system. We have processor, we have memory, we have IO devices, and so on, right? So how do we interconnect them? Processor is within a chip, then that chip needs to be interconnected to other components. Okay, and within a chip also there is multiple components are there. Okay, so there are multiple processors. Okay, as we have seen, multiple cores, and those also need to be interconnected. So we can think wires is as simple as a set of wires or number of wires, and their purpose is to carry signal from one device to another device or one component to another component. As simple as that. We can think of multiple parallel wires at top level, right? Of course, this is more than that, but at this point in time, let's only visualize it as parallel wires. Okay, then we have Ethernet. Ethernet is essentially local area networking technology. Okay, and it carries, it can carry anything. Okay, or say for example, internet packets, right? Instead of internet, you can use any other packets, right, if you want. But the whole, and this is the de facto technology. When I say de facto, it means a layer 2 all other technologies have become obsolete since Ethernet has come. Like earlier, there was token ring, token bus, and many others, right? But still, this is the most popular technology and is being used not only for local area network, but also for, with range extended over, kilometers, many kilometers, maybe 50 kilometers or something, because we have now fiber optical cable, and fiber optics can carry signal to very long distances without any distortion of signals. So earlier there was restriction in terms of length. Ethernet can be used. Actually, we look at that restriction. Okay, but with two changes have happened in Ethernet. First thing is there is no more collision based technology. Packets don't collide with each other, and we have switches. And secondly, if fiber is used, then signal can travel for long distance without distortion. So we look at some of these aspects. Okay, and then desktop will have number of ports to connect IOs, and then there are sensors, right? Because as we discussed in the last class, that temperature is one of the constraining factor. Okay, if temperature of a part of chip or different chips go up significantly, then the system will malfunction. So that is to be monitored continuously, and based on that, various parameters are to be adjusted, say operating voltage or clock frequency, etc. Now, number of sensors in desktop are only few. For example, air temperature sensor, battery sensor, and fingerprint sensors. Now, as part of assignment, you need to look at your mobile and see how many sensors it has. So, for example, mobile will have accelerometer. It may also have many other sensors, right? Uh, which a desktop may not have. Okay, GPS, for example, is very important component of a mobile, because I mean, many applications are based on that, like you can do navigation, etc. But on the other hand, desktop is stationary, so you will not see mention of a uh, GPS sensor or GPS interface here. Okay, all right. So let's look at each one of that. Now, for the processor is i9-10900K. It has 10 cores. In the last class, we studied why do we have multiple cores nowadays, right? The reason, of course, I mean, we studied because of power wall and temperature wall. Essentially these two constraints are there, which forces companies to go for multiple cores. So it has 10 cores. Okay, this and it has interface for Wi-Fi 6, and we see earlier that Wi-Fi 6 is mostly, this is the recent one. Okay, all right. Okay, all other things are okay. We'll discuss the USB 3.2, which is also latest. Uh, all right. So we'll main thing to remember is that it has 10 core uh, technology. All right. So number of cores are 10 and number of threads are 20. You will study in OS class what threads are. At this point in time, you can think thread is lightweight version of a process. Okay, so a process that you are running or program you are running can have multiple threads if you can fork it to different cores. So it means that 20 such threads can run over 10, 20 threads can run over 10 cores. So when we say 10 cores, it means that 10 processors are there inside a chip. Okay, all right. Uh, so 10. So the question is that are they similar? Are each one of these, like these two are similar, these two are similar, so all of them are similar or different? Now you have to see this for your own desktop or laptop you're using and see whether those, do a little bit of googling and find out whether they are same or different. Okay, next thing is that you're a programmer, all of us have got to write programs, right? So how can you use this course? These are available to you, right? Of course OS is using it, it's running different at any point in time there are 15-20 programs that run in a desktop or laptop. So OS is of course distributing those loads, or similarly mobile OS is distributing those loads to the cores. But as a programmer, what all you can do? Okay, how can you write a program that can run over multiple cores? That you think. Okay, uh, and these are all, you need to question yourself, you need to find out. All answers are available in Google, right? So you just need to find out. Okay, and next question is, what is the role of OS in using this codes? Codes are there. Does the OS support these codes? Of course OS has to support. In what way it supports? If OS doesn't support this, who is going to use these codes? Okay, ask this question to yourself and find out the answer. How are these codes interconnected? Of course using bus. But what kind of bus it is? Is it different than the buses that interconnect IO? We'll look at that thing maybe later. And then it has built-in cache memory. So 20 MB built-in cache. So all your laptops or desktop will have cache memory. Okay. What is the rule of what is the use of cache? Anybody? Why we are using cache?
We can quickly retrieve data.
Very good. So we can quickly retrieve. It means that caches are faster. Okay. The question you may ask yourself then is that why do we need main memory then, which is bigger,
Cache
much. Yeah.
cache is limited. Cache is limited. That's
Yeah,
why.
yeah, yeah. Cache is smaller, very right. But why cache is smaller? Why can't you have bigger cache?
Because they are used of they are used of register, and registers are very expensive.
No, 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 they are not. They are different from registers. Registers are different. Cache memory is faster SRAM technology. Okay, and so reason it's small is because smaller is faster. We'll look at that. Okay, we have hierarchy of memory. We'll see in the next lecture some of these aspects. But in general, what you said is right. It's very fast and very small. So when see processor is running at very fast speed, and we need to retrieve data. So in one cycle, we need to one clock cycle. Lot of things need to be done. Now, if you and we'll see in memory hierarchy when we'll study main memory to access data from main memory, number of cycles that the time required will be about 1,000 cycles or even more. Okay, does it mean that if we have to execute one instruction at it in a cycle, we'll have to wait for 1,000 cycles, then efficiency is very low. So what we need to do is that we try to match the speed of access of data or instruction, whatever. Uh, we try to do this at the speed of clock speed. It means that we should reach as close as one clock cycle. Okay, one clock. If we have 4 gigahertz clock, then you can see that time available is very less, and then memory has to match that. So we'll see how. Okay, and this is where we will spend 5 or 6 lectures on cache memory organization. Okay, and within the cache, we will see that there is L1 cache, L1 instruction cache. There is separate cache memory for instruction, separate cache memory, level 1 cache memory for data. So this called L1 data cache. Then level 2 cache, which is bigger than level cache, one cache, and then level 3 cache, which is still bigger. So we have 3 levels of cache. The question again you may ask why, and we'll answer that later. Okay, and did you notice that clock speed is between 3.7 gigahertz to 5.3 gigahertz? And now you can answer this based on what we have studied in last lecture. Why do we need to change the speed of clock? It means that clock speed can vary. And if our task that we are executing does not require faster clock, then we'll run a slower clock because it consumes less power. Okay, and you can do things with whatever maximum performance you can do, right? All right. So no, I didn't get 10 actual internal structure of this processor. So I've taken a quad core processor design, basically which has four processors, and okay, so we can see the structure is very similar here, right? I mean, okay, so there are essentially you can see that 4 processors. Okay, of course processors are not shown here. Okay, so basically there are 4. Oh, sorry, I'm so sorry. This is a processor core. I just forgot. I just didn't see that. There are 4 cores, and each core is attached to instruction cache and data cache. Okay, and there is a level 2 cache. Okay, so each processor has level 1 cache, which is instruction cache and data cache, level 2 cache, and level 3 cache. Also, each processor can access, but it's common. Okay, why it is common, we'll see later. And then there is a system bus to interconnect various IO, so for example, main memory or IO devices. All right. So again, we are looking at very top level. We are not going to detail. And when we study each component in detail, like what caches are, what main memory is, why IO devices are. We'll discuss this. Okay. And then it has other specification like thermal design power. Now you can understand what is thermal design power. We studied in the last class, and that is 125 watt. And this is so the machine has to manage in that power in general, right? That so it is average power in watts the processor dissipates when operating at base frequencies and carries all core cores active under Intel defined high complexity workload. So Intel has defined its own benchmark or own specification that if you are running all four cores, all 10 cores in this case, then maximum power for average load will be 125 watt, and the base frequency is 3.7 gigahertz. Okay, so base frequency is where we define TDP, but it also defines turbo frequency is a maximum frequency you can use. Okay, so this is a maximum single core frequency at which processor is capable of operating. Okay, all right. So how do we increase the frequency of processor? Of course, we have studied in the last class. I mean, basically, we can measure the temperature and we can measure different, say power consumption, etc. If system allows, and if load also demands or the task that demands higher clock speed, then it can be increased. But you know, yeah. So it depends on workload capability and the capabilities of processor and also processor cooling situation. So these points we have discussed in the last class. The question now you can ask yourself, can we increase the frequency selectively on a specific core? So there are 10 cores. Can we run them of different clock speeds? Yes, of course you can do that. You means who? Is it is this control available to a user, or is it control available to OS? Anyone?
OS.
OS, yes. As a user, you don't have all these controls, right? Okay, all right. So because again, when we look at ISA, there's an interface available to us. Okay, and then interface does not say that we can increase or reduce the frequency. Of course, there are some more, some certain things we can control as a user, but not everything. Okay, and then next that we see here is GPU. Okay, graphic processor unit. This is an old name, but but in general, uh, this is a high. This is a processor designed for a specific task, right? Okay, so let's look at difference between CPU and GPU. Okay, CPU in general consists of few cores. So we have seen in this example, we have 10 cores of CPU. Okay, and however, it is optimized for serial processing. It means that one instruction after other in sequential manner, it can be executed. Okay, however, you can create multi-threading and then run these threads in parallel, but in general, CPUs are designed for sequential program execution, okay, with limited amount of parallelism. Of course, there are parallelism in pipeline, also parallelism because of multi-threading, but that's very limited. And these are general purpose, general purpose machine for general purpose computations. Okay, you can do anything out of using a processor, whether word processing or you can do listen to music, sound, multimedia, etc. Right? However, GPUs, graphic processor, GPUs consist of hundreds of thousands of smaller, efficient cores designed for parallel performance. It means that imagine thousand processors connected to each other. Okay, over of course some bus system or some interconnect network. Okay, and their purpose is parallel processing. It means the tasks which are designed, which are meant or which are supposed to do parallel processing can run over GPU. For example, you are doing image processing. Okay, or when you are playing game, then video game, then gaming it requires image processing at very high speed. Okay, and that CPU cannot do that. Now these are the calculations that you need to do at which are very specific, but it has to be done parallelly. Okay, so so GPUs are meant for that. So hardware is designed for specific calculations. All right, all right. So here is an example. This is Intel Xeon E5 2680 V4 processor. It has 64 cores. I mean, this is quite large number of cores. Normally, most of the processors that we see in general laptops has maybe 8 cores or 16 cores at max. And even this recent processor that we have seen, we are studying has 10 cores. Okay, and there is a memory size 256 GB, and bandwidth here is 76.8 GB per second. What is the bandwidth here? When these processors are communicating with each other, what is the maximum amount of data you can transfer is bandwidth. Okay, per second, of course. Now, see these two parameters, if you notice for GPU are different. Now, this GPU has 3840 processors or single precision cores. Okay, and memory size is 12 GB. So memory here is not that important as much is in case of CPUs. Okay, so now memory, of course, there is a without memory you cannot execute, but the amount of data that you need to operate on, the amount of data is of course massive, but each processor need not to have huge amount of memory. Okay, however, what is really requirement is that overall these processors in GPU are executing at very high speed, but they need to also collaborate with each other. Okay, in collaboration in the sense the results are to be collected. Okay, or results have to be transmitted to some device or something. Okay, so that requires the bandwidth to be higher than in case of CPU. So bandwidth is almost like 8 times more. All right, all right. So now again, remember that we are looking at the very top level, abstract level view. We are not going to details. We'll look at GPU design much later in the course. Okay. So now look at this, that if we get application code, okay, then it has sequential components where part of the program is sequential, and some components which are compute intensive functions. So the computing intensive functions can go to GPU, and rest of the sequential code can run over CPU. Okay, and this is exactly what happens when you play game. A lot of activities happen on CPU, and but something related to image manipulation uh, or video processing happens over GPU. All right. Any question?
Sir, how it is that decided that what to send to GPU and what to CPU?
Again, somebody has to do that. And this is what you will study in your systems programming course. So basically, who can do that? Who can create even a code? The question could be, who can create a code that can run over GPU? See, these processors that are here, thousands of processors, need a specific code to run, right? And who is going to schedule there? And what is that code? Because ultimately you have written a program. Who is going to? So of course there is a role of compiler. Okay, there is a role of OS. Because as a programmer you don't have control over all this, right? Okay,
Okay, sir.
I will suggest you to look at GPU design, but in general it's done by OS and also compiler. Of course, a user can write multi-threaded program which can run easily. So there are languages specifically designed for a specific task. Okay, for example, your deep learning or AI computation, because GPU are designed for AI also, right? Or even for video gaming, right? So there are languages available, and then there is a specialized compiler for that. And once that's compiled, then code is available, machine instruction code is available, and that how scheduling of that will happen onto processor is is done by OS. All right. So it's a very specialized area. We'll look at some of these, but in general, to answer the question, is there is a role of OS and compiler. Of course, higher level language is available where you can write the program, where you can do some kind of parallel programming. Then it can be compiled and executed. And at the runtime, OS can do all these activities of scheduling different tasks to different processors. All right. Okay. Any other question?
Sir, here memory is a cache memory, right?
Oh, that memory here, of course, it has to have, I don't know exact structure, but I'm sure it will have, each processor might have cache memory. I don't know exactly what will be structure of memory. We'll
Okay.
see that.
Yes.
Uh, yeah. So basically, each processor has a coupled memory to that. We'll see. We'll see. I don't know at this point in time structure of memory attached to each processor in GPU, but it's very good question. Please hold on to
Yes.
this question. All right. Okay. All right. So the specification of the GPU that's here is as follows. Number of cores are 2560. Giga per second is 7. Now you'll have to see what giga are. You can Google it and find out. Is related term related to image processing. Okay. Or if you're doing this, you will do this course maybe later. Then base clock frequency is 1770. Okay. Boost clock is 1605. So again, we are not going to details. Memory speed is given 14 Gbps. Okay. All right. Then other things as defined is RT course, is ray tracing course. Again, this is for kind of image processing. Then there are some tensor cores, which is for AI processing. So when we say that this GPU, it may have cores of different types. Okay, some for image processing or video processing, some for AI processing, some for very specialized next generation shading, etc. All right, but largely all of them are doing concurrent processing. Okay, so that was about GPU. In general, we can think GPU as something which is very specialized, and then we'll have to system has to find out what components can be executed on GPU. Okay, and these have, of course, these need to have uh, high speed communication among each other using some kind of interconnect. Okay, all right. So next thing is memory. Now we see that 2 terabyte, 7200 RPM, 3.5-inch SATA hard drive. Okay, we call it HDD. Now most of us are using HDD. Of course, my laptop, which is 7 years old, does not have HDD. Because of course Apple Mac machines are usually advanced, so at that time it didn't have, because the weight is another thing. If with HDD, weight also goes up, but in general most of the desktop have HDD hard disk drive. It is a mechanical device like as shown here. Okay, it has number of parallel plates or disks. Okay, these are different disks, and in that we have various tracks. These are tracks. There are multiple tracks. Okay, and each track is divided into sector, right? Like here, these are sectors. Okay, now it rotates at certain speed. Okay, and now note that in order to read something from that, it has to be very much controlled, and speed cannot vary. It has to run at the same speed. Okay, so all this run at same speed, and there is you can see here at the top, also at the bottom, we have something to read. It's called read write head. Okay, so basically it's a magnetic material. In magnetic material charge, each bit can be there as a something that's a charge or uncharged. So each sector that we see is also divided into number of bits, right? It has number of bits. So each bit can charge or uncharged, and when head comes under that particular location, it can read whether it's a 0 or 1. And now we can see there's a parallel reading by all these heads. Okay. Now a limitation of all that is that, first thing is mechanical. So it has limited time, limited lifetime. Second thing that's is there is slow, because cannot spin it at very very high speed. Thirdly, that if you're reading something, then it is sequential in general, right? If you have used, for example, magnetic tape in or cassette in cassette device or music device, right? I mean tape recorder, what we call it, then it's all sequential. I mean, from going to one song to another song, you'll have to fast forward it. Okay, it's all sequential. Similarly, it is sequential to great extent. I mean, of course, there are parallel reading happening into number of plates, but it's largely sequential. Okay, so because if you're reading it something from say some location, then this has to move actually half a rotation up away. If it's half a rotation away, it has to come to the right level, because heads are static, only disk is moving. All right. Now, what is the advantage of all this? Is used for bulk data storage. Okay, is used all right, and is the lowest cost per GB, or is cheapest memory that's available today, because we are not using magnetic tape anymore. So the disk is still being used, but it's very cheap. Okay, so if you look at per byte cost or per bit cost, is the lowest. Okay, and is suitable, but note that it is non-volatile. It means that whatever you write to hard disk remains there. Okay, so there's a reason each machine needs to have non-volatile memory, right? So hard disk is non-volatile, or we can have SSD, which we'll look at next, right? And it also has built-in cache. Now, cache memory, we see it closer to processor, but here also within a device you can create a cache memory, which is semiconductor memory, to increase the performance. For example, when a processor wants to write something to a hard disk, and this is maybe it's a 10,000, maybe 100,000 times slower than processor otherwise will have to wait until this writes everything. But now processor can push it to a cache inside hard disk drive, and then forget it, and then can do its own task. Okay, and once data is available in this cache, then it can write it over uh, to the disk. Okay, so access time is between 5 to 15 millisecond. Note the word this milliseconds here. Okay, so it's almost 200 times slower than DRAM. That's the main memory. Okay, let's move forward. Any question onto this one? Okay, all right, let's move ahead. Then we have solid state drive. Nowadays we have a solid state drive in laptops. So essentially, like flash drive or flash flash stick that you buy, right? And okay, and we have seen that this hard disk drive is slow, and it's also bulky. Okay, so what we can do is that and it's not suitable for mobile devices. Mobiles don't have hard disk drive, because it's of course initial mobiles came with hard disk drive, but it does not have, because it consumes a lot of power, and it's also slow. Okay, so nowadays we have something called solid state drive. Again, this is a non-volatile memory, or it's based on NAND flash memory based device. Okay, and high voltage is able to change the configuration of gate transistor in that. All right. Okay, so we have now SSD. Okay, so now here configuration of this is such that parallelly you can read and write bits or bytes into different different memories, right? So basically parallel, so its organization is done very intelligently such that some kind of parallel reading can be done. All right, now this chart gives you comparison of SSD versus hard disk drive, and we can see that SSD access speed is 20 to 100 microsecond, so it's basically 100 times faster than hard disk. And however, cost of this is higher than hard disk, but over time, once production is more and becomes more popular, then cost will reduce. uh, for example, still it's almost 10 times. Okay, now reliability of this is higher than hard disk drive because it does not move, it's semiconductor based, right? Wherein hard disk drive is mechanical device, so reliability is lower. However, there is only one limitation, that it can do only finite number of writes. It means it can do only 3000 writes. So if in the flash memory that you have, you write more than 3000 times, there's a possibility that it may not work. Okay, and it has low power consumption. So this is the comparison. You can go through chart. Okay, and apart from that, it also have something called obtain persistent memory. Now when we, and again this is non-volatile. Now this is a new kind of memory that's coming up. Intel is not only company that has developed it, but it still is in what do you call that, is becoming popular, right? So not many laptops you will find this Optane memory, but now Optane memory is faster than SSD, okay, or flash memory is faster than that, and it's non-volatile. It's based on phase change technology, right? Okay, so now you need to look yourself, what is the phase change technology, what is the phase memory in general. Okay, because SDRAM and DDRAM both are based on whether capacitor is charged or not charged, that kind of. But this is the phase change, this is a different technology altogether, right? So read about it. And it's less expensive than DRAM. DRAM is main memory, right? We'll look at that. uh, so it's 10 times faster than, faster means that time to read is 10 times lower than that, that is for NAND drive or SSD drive. Okay, so so it means that it's a better in terms of access time than SSD. Okay, so obviously we are trying to this kind of hierarchy because we want to reduce the access time, and also we want to have more and more capacity. So we'll see how to do that in maybe next class. And then we have main memory. Okay, it's called DRAM basically. And one type of that is SDRAM, synchronous DRAM. Okay, now this is a volatile memory. Okay, now capacity has got to be higher. Okay, because bulk of the data will reside here. Okay, and then but its speed is slower than cache memory. So on top of this we have only cache memory and registers. Okay, now cache memory we are not discussing it here. So basically what we see, this is a main memory. It's called main because heavily used. Okay, and data comes, obviously data has got to be there in a storage device, SSD or HDD, at the time of boot up, or if your file size is very very large or database is very very large, it has to be there in hard disk drive or SSD, right? From there you can bring it to main memory, and then main memory it can go to cache, and then it can go to registers or processors. And similarly we have GPU is also connected to main memory. All right, okay. Now this shows DRAM chips. Where is DRAM chips here? DRAM banks here. These are all chips, DRAM chips that are connected to a processor using some bus. This is a bus here. All right. Okay, then comes bus. Bus is nothing but parallel wires we can think of, and there are various kind of buses, right? And the one that this desktop uses is PCI bus. Okay, so this is a bus that connects to a USB driver, various USBs we have seen USB ports in every desktop, laptop will have USB port. It can connect to, monitor where you can see, you can visually see things. So there has got to be graphics adapter, then it's connected to disk drive or hard disk drive or SDD. This again through IO. Okay, so this bus is connecting various components of computers, and then there is a internal system bus. Okay, within the chipset, right? So it works at very fast speed. Okay, and then there's something called memory bus. Okay, which connects to memory. So processor memory is connected over memory bus, and there is of course a bridge, and then that connects it to PCI bus. Okay, so this you can think that the main memory bus is faster. This is comparatively slower. We'll see that these are more these in more details later. And then we have Wi-Fi and Ethernet. Ethernet is of course de facto LAN technology, and various speed it can operate from 10 megabits per second to gigabit per second. Okay, 48-bit MAC address. We'll study that CSMA CD protocol. And it's very is a mature technology. And then Wi-Fi we have discussed in general. So it will have Wi-Fi chipsets and Bluetooth chipsets. So this is all about what we have discussed today. We have we have a CPU. Okay, okay. So we have processors. Okay, these are what is shown here is 8-core processor. Then we have GPU. Okay, then we have some accelerators, or similar to GPU. GPU is a kind of accelerator, basically to accelerate execution of some parts. So we can have also accelerators. Then we have main memory, which is DRAM. Then we have persistent memory or non-volatile memory. We can have HDD or SDD. And then we can have a high-speed network. We can have this is Bluetooth or Wi-Fi, and then Ethernet port. Okay, so that's all about a desktop in general from top level. We have not discussed many other components a desktop may have. It may have voltage stabilizer, it can have keyboards, mouse, and all that we have not discussed in, in this class. All right, any question?
Sir, in the bus part,
Mm-hmm.
if one of the buses fails, is there a way like the connection will get disconnected, right? So is there something else done to prevent this?
So we'll have to see the design. Okay, we'll have to see. So most of the computers are not designed for that level of reliability that you are asking for. Okay, so it's based on the concept that these things will not fail. Okay, with certain lifetime. Okay, however, you can always design a processor that will have multiple buses, multiple processors, multiple ways of tolerating failures. Okay, so there can be some limited amount of fault tolerance in any design, which is not visible from outside, but there is always, even when we communicate data, there is some extra error correcting bits, etc. But in general, in a system there are a lot of components that are made highly reliable. Okay, so for example, this wire, these buses are actually not so active device, not many transistors etc are there. So the probability that will fail is usually very less. While your question is correct, that how do we design systems which are highly reliable? So we can always design systems which are extremely reliable, uh, by creating redundancies. All right? Okay.
Thank you, sir.
Sir, why RAM modules have higher life cycle than SSD? They both
Uh,
operate on flash chips now.
no, I cannot understand. Can you please repeat?
Sir, why RAM modules have higher life cycles than SSD ones?
High life cycles.
Yes.
Which model? The buses, etc.
RAM module. ये अपनी memory होती है ना.
Oh, memory. Okay. Oh, okay. After 1,000 reads, it cannot. That kind of question. So,
बट सर लाइक आई मेरे लैपटॉप में जो मेमोरी है सर उसकी
हाँ,
सर उन्होंने लाइफ टाइम गारंटी ले रखी है सर और मैंने
किसकी
पढ़ा था सर
किसकी लाइफ टाइम?
रैम मॉड्यूल की सर रैम
So basically, lifetime when you okay, this interesting thing. Lifetime of my lifetime, your lifetime, or processor's lifetime. So when you read warranty, even refrigerators have lifetime warranty. They say they define life of what is going to be life of a component. Okay, so that lifetime is always in terms of number of days or years. Then you just look at that. Then they have designed in such a way is unlikely to fail. However, of course, things do fail. So now if you spend more money, more in R&D to create a system that is not likely to fail, then it's fine. Say for example, when we are sending a you know spaceship, on a spaceship or something that's that will circulate around Earth for, or satellite for maybe 20 years, then you are using the best possible technologies and components that can work for longer period of time. So reliability of that is much higher, the probability of failure. Okay, so you can always spend more money on tech. Now it's again question of how do you design and what kind of money you are going to spend on a device, right? So there's a lot of things are there, but in general every manufacturer said something based on lot of factors, and one factor is of course how much money consumers are able to. Say for example, I may not want a laptop that will work for more than say 5 years. 5 years I will extract whatever I want to do that, or but you see, these 2 years I got for my laptop are actually bonus. So I am not willing to spend money to buy a laptop which will work for 20 years. It's not really required because technology is obsolete by that time. Okay, you got my question. So reliability is created by manufacturing process. Again, how do you, and of course system components can fail. Okay, and there are of course reliable technology component. For example, SSD is reliable for the long period, but the question is that how many times you do read. If you do more than 1,000 times read, then it may not work. Okay, all right. Any other question?
Sir, like, can you please explain what that chipset means in that? I think one of the earlier diagrams there was.
Chipset. Okay, chipset is nothing but set of chips exactly for a Intel comes out with chipset for a processor. So they come out with, see, this processor. Okay, this processor, right? Okay. Okay, so there is a processor, and along with that it will come out with number of other chips, supporting chips, right? So all that we call this a chipset here, right?
Sir, yeah, but again, I think again one more diagram before it had shown like a pictorial.
Okay, here.
Yes, sir. This one, Intel 400.
Oh, okay. So basically, chipset is all along with this. See, this alone cannot work, right? So this is also part of set of chips that if when a processor is comes out, it has to come out with set of chips which will interact with it, or it can be interconnected with it. Okay. So these are all other for example, this another is this chipset which will support all USB and with certain functionalities. Okay, and there's a different ways you can design chipset around a processor, and different companies do it different. Intel chipset would be very different from maybe for ARM. Okay, but in order to make functionality complete, because processor alone you will not buy, along with it, it has to work with USBs, it has to work with hard disk drive, it has to work with memory, and then there has to be supporting hardware for that, hardware software for that. So chipset supports that in general, right? All right. So here the chipset that's shown here has certain functionality. For example, it will support PCI bus. It will also support Wi-Fi. It will have certain number of USB cables. It will have interface to LAN. Uh, HD audio, and so on. Okay. All right, folks. See you tomorrow then. And tomorrow the class will be a little longer. It'll take about maybe 1 hour 20 minutes or so. Okay. Thank you. Bye.
Bye, sir.
Bye bye.